Physics chapter 29 theory video 5 randomness and radioactive decay. So now if you take a Geiger-Müller counter and start detecting the radiation that comes, that is the alpha particles, beta particles or gamma ray photons, you would see that they don't come in a regular pattern, even though you can adjust it to now if you take a weak radioactive sample that gives out about one detection per second, then you can hear it properly. But it does not go like tick 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 in a regular pattern, but it would be dig 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 like that. It is not going to be regular. So this is because it is random, and we can't predict when the next one is going to come, when the next decay is going to come. However, if you take a graph of count rate against time of a sample, you will see that it would have a shape like this. So it is you can remember how the half-life is. So when a sample decays, what happens to the to the time it takes for the sample to half. So now what happens is, the reason why the count rate decreases with time is because a number of radioactive nuclei that are going to be left would decrease. So these fluctuations that are there, it is the curve not being smooth, is because of the randomness of the decay. Because it is random, it shows these fluctuations. It rate decreases because the number of radioactive nuclei is going to drop. So that is the reason why you will get a shape like this. This radioactivity is radioactive decay is random, and also it is irregular. So but there is some predictability. We can get the average rate of the decay. If you take a longer period of time and if you take an average, then you will be able to see a pattern. But still, you will have to repeat the experiment over and over again. Then you will be able to get a brief idea. But still, it might, the next moment, it might not obey the principle that we have developed. Radioactive decay is when an unstable nucleus of an atom breaks apart while emitting radiation and becoming a different, the nucleus of a different element. We cannot predict, and we can't see any changes that is happening, that it is going to decay. That is, there are no signs being shown. So it can randomly happen. So because now when you take an atom, the nucleus is in the middle, and the nucleus is not very close to the other nuclei. Even though we feel that it is very close, it is not. And also all the diagrams that we have drawn of atoms, they are actually not to the scale. Now if you just imagine that the nucleus is a house in the middle of a desert. If you are inside the house, you would be a proton. So the house is the nucleus. The next house would be 1,000 kilometers away. That is the nucleus of another atom. The electrons are about 100, 200, 300 kilometers away. So they actually, the nuclear charges or nuclear attractions have nothing to do with the next house. They are not felt by the other nuclei. Therefore, there is no effect on this decaying process by other nuclei. So it is spontaneous. Spontaneous means it happens without any other effect. So the heating or increasing the temperature or increasing the pressure will not have any effect on on a radioactive material to decay. It does not have any effect on it. Then random means it will not, we cannot predict when it is going to happen. So there are two reasons for each one that you will have to remember. Nuclear decay is spontaneous because the decay of a particular nucleus is not affected by the presence of other nuclei. And it cannot be affected by chemical reactions or external factors such as temperature or pressure. Then it is random because it is impossible to predict when a nucleus in a sample is going to decay, and each nucleus in a sample would have the same chance of decaying per unit time. So we are talking about radioactive materials. Let's write a note on that before moving on to the next part. Write down. Radioactive decay releases alpha beta particles or gamma ray photons, which can be detected by a Geiger-Müller tube. When observed, we will understand that these detections are irregular in pattern and are quite random. If a count rate against time graph is drawn for a particular sample of radioactive materials, we would obtain the following graph. It shows that the rate is reducing because the number of radioactive nuclei that are left is going to decrease. So as a result, the count rate would decrease. The fluctuations are caused by the randomness of the decay. Fluctuations are caused by the randomness of the decay. So you understand that because the number of nuclei, radioactive nuclei decreases, so that means only a lesser and lesser alpha and beta particles would be, alpha, beta and gamma radiation would be produced. So the count rate is bound to reduce. However, by repeating the experiments with similar samples, we will be able to get a general idea as to how the decay takes place. However, this is not a certainty. Leave a line and write. Radioactive decay is spontaneous as we cannot predict how the individual nuclei would, how and when the individual nuclei would disintegrate. They are not affected by the nuclear force of the neighboring nuclei, because in an atomic scale, the nuclei are incredibly incredibly placed apart and would have no effect on one another. Therefore, we say that nuclear decay is spontaneous and random. Leave a line and write nuclear decay is spontaneous because, number one, the decay of a nucleus is not affected by the presence of other nuclei. The decay of a particular nucleus is not affected by the presence of other nuclei. Number two, the decay of nuclei cannot be affected by chemical reactions or external factors such as temperature and pressure. The decay of nuclei cannot be affected by chemical reactions or external factors such as temperature and pressure. Then write down nuclear decay is random because, number one, it is impossible to predict. It is impossible to predict when a nucleus in a sample is going to decay. Number two, each nucleus in a sample has the same chance of decaying per unit time. Now we are going to discuss about the mathematics of radioactive decay. So that is, we have to involve calculations into this. So this is what we are going to consider here. Now, because these nucleus and nuclei and these atoms are very, very small, even a small speck of radioactive material, even a small dot of radioactive material would have about 10 to the power 15 nuclei. So as a result, we have to consider the average number of nuclei that we expect to decay in a particular time interval. So that means we are going to take the average decay rate. Because we can't actually take an individual electron, individual nucleus and consider how within what time we expect it to decay. It is not possible. That is because we cannot predict, because it is random and spontaneous. We can't say when it is going to decay. Then some nuclei are more likely to decay than the others. For example, carbon 12 is very much stable. However, carbon 14 would decay gradually over thousands of years. Carbon 15 nuclei, on the other hand, will only last a few seconds. So it has a half-life of few seconds. So that is what you need to understand. So if you want to take a measurement, so what we do is we take a large number of nuclei and then calculate the averages. Now, for example, if we take 1 million parts of nuclei of a particular isotope, if we can figure out that over 200,000 have decayed during a certain period of time, so let's say it is an hour. So we know that the decay rate is 0.2% or 20% per hour. That is, out of a million, 200,000 have decayed. That is 2 upon 10, that is 0.2 or 20% has decayed. So in this situation, in this scenario, if we take one sample, it would give 200,000 as the answer. However, if you take another sample, it might give you 199,000. Then the next one might give 205,000, something like that. So we have to take many samples and get an average. So it is going to be, if we take much of as many samples as possible and get an average, so it is going to be likely that it is closer to the actual, or we can get a little bit of a constant value, a reliable answer rather. So the probability that an individual nucleus will decay per unit time interval is called the decay constant, and we have unfortunately given the term lambda for that as well. So don't misunderstand this with the other lambdas that we have spoken about. Here the decay constant is lambda. So the decay constant here, lambda is equal to 0.20 per hour. 0.20 per hour, that is how we write it. This decay per unit time interval, that is lambda has units of h minus 1, or it could be per second, per day, per year, anything. So the activity A, the activity A of a radioactive sample, so if we refer to the A as activity, and activity means the rate at which nuclei decay or disintegrate. So that is another factor that you need to understand. Activity is, we measure activity in decays per second, or h minus 1, or day minus 1, or s minus 1, anything. And decay per second, there is another unit for that. Decay per second is 1 becquerel. I suppose you can learn, or you can remember from O levels, this was named after Henry Becquerel. So this unit, 1 becquerel, is what we refer to as 1 decay per second. So the activity of a sample will depend on the decay constant of that isotope that we are going to consider. Higher the decay constant, that is the higher the probability that the individual nucleus per unit time interval, so that is the greater would be the activity of the sample. That is, if there is 500 million becquerel, so that means 500 million nuclei would disintegrate within a second, and it is obviously more than 200,000 becquerels. So that means only 200,000 nuclei would disintegrate within the same time. So we say it will also depend on the number of undecayed nuclei n present, because if the undecayed nuclei n reduces, then it would reduce as well. So as a result, we can get an equation for activity. For a sample of n undecayed nuclei, we have A equals negative lambda n. Negative sign comes because of the number of undecayed nuclei is going to reduce. So in this, lambda is the decay constant, n is the number of undecayed nuclei. So activity A can be taken in the form of A equals negative lambda n. If you want to figure out only the magnitude of the activity, then you can disregard the negative sign. But if you think in the whole concept, then you have to use the negative sign as well. Then the activity can be considered in a different sense as well. That is, number of alpha or beta particles emitted from the source per unit time. So then we can write the activity as A equals delta n divided by delta t. Delta n is equal to the number of emissions. So in the earlier situation, we had n referred to the number of undecayed nuclei. Here it is n referred to the number of emissions or decays in a small time interval of delta t. So that is another equation that we need to take into consideration. So now let's look at this worked example. A radioactive source emits beta particles. The source has an activity of 2.8 × 10⁻⁷ becquerels. Estimate the number of beta particles emitted in a time interval of 2 minutes. State one assumption made. So the values are given, the activity has been given in becquerels. So if we write it in if we write the details, the values that have been given, then it is going to be really easy for us. A is equal to 2.8 × 10⁻⁷ becquerels, delta t is equal to 120 seconds. So then we can figure out how many beta particles are released. A equals delta n over delta t. Delta n is what we need to figure out, that is A into delta t. A is Activity is 2.8 into 10 to the power 7 multiplied by delta t is 120. Then we have 3.36 into 10 to the power 9, 9 beta particles that is being emitted during this particular time period. So then they are asking, state one assumption made. So we have to assume that the obviously the decay remains, the decay or the activity, the rate of decay or activity remains constant over this particular period of 2 minutes. Then let's look at question number 6. A sample consists of 1000 undecayed nuclei or nuclide whose decay constant is 0.220 per second. Determine the initial activity of the sample. Estimate the activity of the sample after 1 second. So, we know an equation A equals lambda n. A has been given. We have to find A because they are asking for the activity. Activity is equal to lambda is 0.20. 20 into 1000. Decay constant has been given as 0.20 per second, so it is 0.20 multiplied by n is the number of undecayed nuclei, that is 1000. So we have 200 becquerel as the answer. So the activity is going to be 200 becquerel. Then after 1 second, so that means after 1 second, that is 200 becquerel means per second 200 has decayed. So after 1 second we have to expect 800 nuclei to remain undecayed. Then we have to find the activity at that time. Then A is equal to lambda n. Now it is going to be, still the activity is going to be 0.2 multiplied by now the undecayed sample would be 800 multiplied by decay constant is 0.2 rather, multiplied by 800 would give you 160 becquerels. However, in reality, this is going to be a little higher than this because the rate of decay will decrease with time. Then that is a continuous process. So all the time it is going to reduce. So as a result, less than 200 nuclei would decay during the first second. And in the next second, less than 160 would decay, etc. So that is how it is going to be. Then count rate. So now we are most often interested in finding the activity of a radioactive material. We can't measure it directly because these are things that we cannot see, and also we cannot detect all the radiation emitted. Why? Because we can't place detectors in a 360 angle. Some will escape us, and some may not even reach the detector surface. Some would be absorbed only by the detector itself. Then whatever the materials that this detector is made up of, they might absorb some of the particles as well. So like that, there is a loss of activity that can be detected. So a fraction of the activity would be lost. The remaining fraction is only what we detect. So the further away we place the counter or the detector, lesser would be the rate. So then the actual count rate that we obtain is lower than the activity A. So if we know how efficient our detecting system is, then we can deduce the real activity from the count rate, which is going to be named R. So then also there are radioactive materials around us. For example, radon gas. They might also give us a reading. So we might misunderstand that to be the activity that is coming from the sample that is provided, but it is coming from the background radiation. So we have to subtract the background radiation from the count rate to get the corrected count rate. So these are some things that you need to understand. And before we move on to the next part, let's write down the note and do the questions. Write down that the mathematics of radioactive decay. Radioactive decay is random and spontaneous. As a result, we need to obtain average values to get a clearer picture of what is happening. If we take a very large number of nuclei and take average values repeatedly, we will be able to obtain a reliable answer. Leave a line and write the probability that an individual nuclei will decay per unit time level, decay per unit time interval rather, is called the decay constant lambda. Leave a line and write, for example, if 200,000 nuclei decays within an hour from a sample of 1 million nuclei, its probability of decaying is 0.20 or 20%. As a result, we have a decay constant of 0.20 per hour, 0.20 h minus 1. Decay, leave a line and write, decay constant can have units per second, per hour, per day, per year, etc. Leave a line, put a star and write down the activity A of a radioactive sample is the rate at which nuclei decay or disintegrate. The activity of 1 decay per second is 1 becquerel. An activity of 1 decay per second is 1 becquerel. 1 becquerel is equal to 1 BQ equals 1 S minus 1. Higher the decay constant, greater would be the activity of the sample. It also depends on the number of undecayed nuclei, capital N. When N is lower, activity will also drop. Therefore, for activity we can get the below equation. A equals negative lambda N. A is the activity, N is the undecayed nuclei, and lambda is the decay constant. Also, activity can be thought as number of alpha or beta particles emitted from the source per unit time. Therefore, activity can be written as A equals delta N upon delta T. Delta N is in this particular situation, it is number of emissions per unit time, and delta is the time. Leave a line and write. Um, the 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 rate of decay when being observed using a detector only a fraction of the radiation would be detected by it, because some will escape past our detectors and some will be absorbed by the sample itself. Therefore, the count rate R that we obtain would be lesser than the activity. If the efficiency of the detecting system is known, then activity would be calculated from R. If the background radiation is significant, that needs to be deducted from the corrected count rate. I hope that makes sense. If it did, please do question number 13, 14 and 15. After that, we'll move on to the next part in the next video.